Here's the agenda today. As many of you don't know who is Linaro, I'll explain about who we are, then VirtIO today from OASIS aspect, and finally a challenge of the VirtIO in terms of the overhead. Introduction. My name is Shimada, country manager of Linaro, Japan and Korea region. I've been working in the semiconductor industry and embedded in IT area over 30 years, spending my life studying and working in both Japan and California. I also work on SOFI, closely working with ARM, since SOFI was founded by ARM and Linaro a few years ago. Now we have more than 150 member companies today. And Linaro is a company who provides ARM ecosystem solution, founded in 2010 at Cambridge, UK, and most of engineers are from previously ARM software department. We develop, test, deliver ARM-based solution and technologies based on the open source software. We target automotive area with the Linux kernel solution, security, CI/CD, toolchain, and virtualization. Among many engineers at Linaro, many of them work on Linaro, emphasized on the Linux kernel maintenance. Of course, we do bootloader, real-time OS, security, Android, virtualization, including VirtIO, compiler, and so on. Linaro is a top contributor in the Linux community, as the right side of the histogram shows. And also regarding VirtIO, Linaro is closely working with Panasonic to jointly enhance VirtIO. Thank you very much. I always appreciate Panasonic for the collaboration and partnership. And our board members are ARM, Google, and Qualcomm. So actually, we also emphasize on Android. We support customers from research stage, software stack, development for POC, consultation, deploy and implementation, and also long-term support. Particularly, automotive requires long-term support. 10 years or even longer, depends on the product. And Linaro helps automotive companies to work on LTS for Linux and Android. We also see many companies are concerned about the CRA as the recent hot issues in many industries. All products shipping to the European market requires going through the process and get a certification of the CE mark. This is really a time-consuming work, and that often requires a dedicated software team in the company to go through the process for each single product to ship to the EU market. Linaro is an European company and well familiar with the CRA and the process and how to pass to obtain the CE mark certification. Linaro has a program to help the support customers. If you want to know more about CRA and the process, please let me know. Now, moving on to the VirtIO topic, VirtIO today. I will cover the current status of VirtIO first, then role of OASIS and the current status in terms of VirtIO, then role of AGL from the automotive perspective. The VirtIO specifications are determined by OASIS. You can find them on the website, and Linaro makes a big contribution in OASIS. The Virtual I/O Device Technical Committee with the OASIS is responsible for defining and approving the VirtIO specifications. The specifications for each devices are eventually merged into a Linux kernel So VirtIO is constantly evolving. I hear some people think that VirtIO is done by AGL, but the specifications are defined by OSIS. And the AGL is responsible for implementing and operating them, and feedback to OSIS. Regarding OSIS, the first official version, 1.0, was released in 2016, where initial items such as block, network, GPIO, I2C, and so on were released. And the version 1.1 was released in the year of 2019 with the VirtIO entropy, input, VSOC, crypto, and basic GPU. So we are particularly considering devices aimed at automotive applications. Relatively recently, VirtIO Sound, VirtIO GPU, and the other devices have been added as V1.2. The OSIS is working on the enhancement toward automotive functions and increasing the devices. Currently, V1.3 was released a while ago with several new devices. The latest one is V1.4. That was just released last month, April. And that includes VirtIO RTC, VirtIO CAN, VirtIO Media, VirtIO Video, VirtIO SPI, and VirtIO Wi-Fi, and others. So this is a summary list of all VirtIO devices as of today. And just one information, VirtIO Video and VirtIO Camera are planned to be merged into the VirtIO Media, maybe VirtIO version 1.5 or maybe later versions, just for your information. So to summarize, the OSIS in the left develops the VirtIO specification and the new devices and constantly expand the standardization. While AGL in the right will implement VirtIO and provide feedback to OSIS. So that's the current status of VirtIO. Next, we move on to the VirtIO challenges. VirtIO is a virtualization technology. In conjunction with the hypervisor, it generates overhead compared to the native. And particularly in between the guest OS and the host. This is a concern when considering adopting VirtIO in the automotive system. And the overhead causes latency in each area compared to the native environment. This latency is something that needs to be taken into consideration, not only in ADAS, but also IVI. It is necessary to find out where is the bottleneck. Is that the guest OS, hypervisor, or hardware? Which layer is the bottleneck? In order to understand how much of the latency, benchmarking to measure the latency is important. So what is the mechanism that causes latency as follows? So I pick up the three examples. The first, in the left, there is I/O path delay. This is because VirtIO is virtualized, which means that the communication path from the guest OS to the hardware is longer. The overhead is caused by processing via the hypervisor and operating the VirtQ to exchange the data between the guest and OS, which takes time. As a result, high latency. Second, in the middle, is resource contention or resource competition. Competition occurs when multiple VMs are sharing one single resource, such as CPU or memory. And as a result, when a high load task is executed on one VM, all other VM are slowing down. Also, there is interference when non-critical tasks prevent critical tasks from executing. And the third, in the right, there is scheduling uncertainty. Since the hypervisor controls VM scheduling, unexpected delay occurs from the guest OS side. And where the latency occurs, I pick up the three examples here on the page. The first is command submission, which is the bypass time between when the guest OS is issued a Vulkan command to the GPU and when it reaches to the physical GPU on the host OS. That is context switch cost. Or VirtIO transaction flow, guest OS transmit data to VirtIO and interrupt for notification of completion, I mean context switch. The second, in the right, is memory mapping, which involves synchronizing and copying the video memory between the host and the guest. That is shared memory efficiency. The third is interrupt, which is the overhead. For example, of notifying the guest OS that GPU processing has finished. So those three are kind of good example, I think. Now, I've listed the latency measurement items for specific use cases, IVI and ADAS, that I pick up a few examples here. The first IVI on this page, here they picked up 5 examples. The first is frame time variance that measures the jitter of each frame variance. Specifically, we measure the frequency of outliers to prevent startling the meter needle. The next is WCET, or the worst case execution time, which identifies max latency. For example, within 100 milliseconds or 50 milliseconds or something like that. The third one is a measurement of zero copy efficiency, which measures the efficiency of shared memory between the host and the guest. The fourth item is startup flip latency. This measures the delay from power on displaying images on the display for the use cases such as rear camera images. And the last one is the mixed criticality. This measures whether meter drawing latency increases when load on IVI is high. That's for the example of IVI. And the next one is use case for ADAS examples. I pick up kind of 3 cases. The first one on the left is a measured sensor data pipeline latency. This is evaluate whether the data transfer overhead caused by the virtualization leads to delays in pedestrian detection. The next one in the middle is end-to-end latency, which looks at the total time from when the obstacle is captured on the camera to when it is detected by the GPU and the warning is displayed on the screen. The third one in the right is priority inversion, which looks at the GPU scheduler to see if a low priority VM is monopolizing the GPU and interfering with the higher priority ADAS processing. Those are the 3 examples of ADAS. In conclusion, this is the last slide. When deploying VirtIO in the automotive system, if you are concerned about overhead and latency, here is the solution. The first, in the left, you need to measure the latency at each item by benchmarking to understand how much of latency on the specific platform. And the second, understand acceptable latency range for the items to figure out the gap. And finally, optimization. That is to shorten the WCET, the worst case execution time, to make the latency within the acceptance level. And Linaro is good at doing the latency benchmarking and optimization to shorten the latency to help you. That's all for my presentation, and thank you very much. If you have more questions, or actually you can also download this slide by scanning this QR code, and also you can also send me an email anytime. Thank you very much. And also, I will be at the reception also with my colleague, Lei, just presented just before this session. We'll be there. So we are really open to talk to anybody. If you're interested in, please do not hesitate to come to me and talk. Thank you very much.